Hey everybody, welcome back to another review video. This one's going to be for Algebra 1, specifically Module 3. Module 3, Topic 1, which is all about exponentials and their graphs, their transformations, setting up equations. We have another topic in Module 3 about exponentials as well. That final is going to look a little different. That exam is going to look a little different than this. But for this one, we're just going to go back to the old review packet. I'll do the left side. You do the right side. If you complete it, you can use it as notes on the test. I think I start to maybe sense some people losing focus in this video already. Here, I have an idea. I think I can maybe help you guys out with your Zoomer brains. Yeah, let's just go ahead and get started with the review here. So the first problem we have is two tables, and they're asking us to write exponential functions about these tables. Okay, so we're looking at the situation and we're writing the exponential function. Now, the thing we have to remember for this is the base form of an exponential equation. I'm going to write it as notes right here, and then I'll actually end up doing the problem. But here's what it looks like, right? So you have something f of x, right, just any function, is equal to, we have this letter a out in front times b to the power of x minus c plus d. If you don't have this in your notes somewhere, I would write this down because it's very important. The starting value is a. So wherever you're starting with, so when x is 0, when time is 0, what are you starting with? Okay, we'll see those in this problem specifically. Another way to think about that is it's the y-intercept before any transformations at least. We have this b value, which is what we call the rate or the ratio. It is basically what you're multiplying by each time, right? What do you have to multiply by to get to the next thing in the situation? You have this c value up top. This is your horizontal translation. Horizontal translation. You got to remember that in this one, it's opposite. So horizontal means left and right. Oops, sorry. Horizontal means left and right. The weird part, though, is that left is plus, but right is minus. Okay, so it's opposite what you might think. So this c is doing the opposite thing. The reason why we write minus c is because of this opposite nature, right? Like if this is x plus 3, that shifts to the left 3, okay? The reason is you're impacting the input, so the input has to change by that amount to make up for it. Left and right is x, okay? And then finally, you have this plus d at the end. This is your vertical translation, okay? That's up or down. And importantly with this one, it just follows the rule. Plus is up and minus is down. So it does what it says, okay? We won't need C or D for this function or for these tables, but we will need A and B, the starting value and the rate, okay? Well, the starting value is what happens when time is 0. And so in this first scenario, without even reading the problem, the savings account over time, money is exponentially growing. I can tell you that my A value is going to be 5,000, right? That's going to be A in this equation. So all I really need to figure out is B, right? The rate, what I'm multiplying by. And so really what I'm trying to figure out is what do I have to multiply by to get from 5,000 to 5,250, okay? Well, the way to figure that out is to kind of think about it backwards. If I want to figure out what I'm multiplying to get from here to here, I could just do the reverse and divide, right? Whatever I divide by to get from the second one to the first one is what I'm multiplying by to get from the first one to the second one. I don't have my calculator up on this, but I have it on my phone. I'll tell you right now that 5250, so 5250 right here, divided by 5,000 is 1.05. So that means that B is equal to 1.05. That's similar to the challenge problem we did with my salary going up by 5%. Well, my final answer would be the combination of these two things. I know what A is, so let's just say that f of x is equal to, and I'm going to do it in this line. I'm running kind of out of space. Sorry, the Subway Surfers is taking up my room. We have our starting value is 5,000, and our rate is times 1.05 to the x power, right? And that's our answer. So 5,000 times 1.05 to the x. Let's do it for this one as well. So same idea, f of x equals a times b to the x. Our starting value when time is 0 is 1, so that's a. And then what do I have to multiply to get from here to here? Well, this one I can do in my head. 1 to 30 is just times 30. And so that is b. So my final equation is f of x equals 1 times 30 to the power x. And that's how you would do it, right? By the way, if you are tripling the amount of Skittles in the jar, that is a crazy amount very quickly. You would have, I don't even know how much 2,700 Skittles would cost. I think that would cost a lot. How many Skittles are in a regular pack of Skittles? Leave a comment if you know the answer. Okay, I'm genuinely curious. I don't know. All right, let's go to number 2. So super similar idea. This time you just give me the answer for what equation matches this scenario. Okay, so once again, a times b to the x. A is the starting term. B is what you're multiplying by each time, or what your rate is. So f of x equals this. In the case of this situation, the first month is 3 comic books. Okay, so that's the first starting value. And then after that, he increases by a constant ratio or rate. We just have to figure out what that is. Well, to get from 3 to 12, that is times 4, right? You could do 12 divided by 3 to make that, but I can just sort of see it in my head. And then same thing, 12 to 48 is also times 4. That means that f of x is equal to my starting value, 3, times 4 to the power x, which looks like answer B. Nice. Cool. All right, moving on. So those last 2 problems were setting up equations if you're given a table, kind of like the geometric sequence in Mathia. This time, though, we're going to jump to something a little bit different. This one is all about using exponent rules. So what you have to remember here, the big idea with this whole set of questions is that x to the 1/2 power is the same as the square root of x. And x to the 1/3 power is the same as the cube root of x. I don't know why we don't write the 2 here, but there is a secret hidden 2. The thing you have to remember is that this is the square root. The number that you think of when you square something is 2, right? Like you raise it to the 2nd power. And so these are inverses of each other, right? Like the square root is the inverse of square, and so it's the 1/2 power, which is the inverse of 2, at least multiplicatively. Okay, so with this one, and with these problems, we're just going to simplify each equation and then using a rational exponent, meaning using a exponent that's a fraction, right? Rational just means fraction. So we're just going to rewrite each so that it has a fraction exponent. So in this case, it's going to be 2 to the power of 1/6, right? This pattern continues. And that's it. In this one, it's going to be 7 to the 1/2. That's also it. But this one, it gets a little bit trickier in C because we got 2 things going on at once. Okay, if you answer the problem on the door, you might have an idea of how to do this one. Anyway, so I can see that the inside here, I'm just going to look at the inside of the parentheses first. It says the 4th root of 5, or the quad root of 5. Well, that would mean that 5 is being raised to the 1/4 power. And then this whole thing, this whole inside right here, is being raised to the 8th power. And so really, these 2 are the exact same equation, just rewritten. And then we know about the power to a power rule, meaning when you have an exponent raised to an exponent, or a power raised to a power, you multiply the exponents, right? You multiply the exponents. Subway Surfers guys died? Wow, cringe. Did you use an extra life too? No. Anyway, in this case, we have 5 to the 1/4 to the 8th. That's the same as 5 to the 1/4 times 8. And then 1/4 times 8, well, that is the same as 8 over 4, which is the same as 2. So really, this is just 5 squared, which in total, your final answer is 25, because that's what 5 squared is. Cool. So think about these just to remember this. X to the 1/2 power is the same as the square root, and the pattern continues. X to the 1/3 is the cubed root of x, and so on. All right, so in this one, we have to go backwards. So we're given the radical form, and we want to rewrite it, or sorry, we're given the exponent form. We want to rewrite it as a radical. Radical is just, it means it has this symbol somewhere in it, right? Well, I can use the same exact logic from these last problems to know that if h is being raised to the 1/7, that's the same as the 7th root of h, right? And that's the answer for that. It gets a little bit more tricky when you look at these two, so b and c, because there's actually two things going on in the fraction. This is 12 to the 7/12, okay? And the tricky part about this is to note how we can rewrite this fraction up top. Okay, here's what I'm going to say. I know that when you multiply fractions, you just multiply top to top and bottom to bottom, which means that this is the same as 12 to the 7 times 1/12, right? 7 times 1/12 is 7/12, right? 7 1/12 is 7/12. And I'm going to rewrite them as being multiplied because I know about the power to a power rule, right? When you have a number raised to an exponent, raised to an exponent, you multiply the exponents. And so really, this is the same as this, 12 to the 7th to the 1/12, which I know is weird, but because I'm raising an exponent to an exponent, I multiply, right? Well, 12 to the 7th is just 12 to the 7th, and then the 12th power is just the 12th, or sorry, the 1/12 power is the 12th root. And so this is your final answer. The 12th root of 12 to the 7th, right? I'm going to do a little bit of notes here. If you want this generally, it's something to help you. This always works, right? If you have any number x, so any number x that is inside a radical, we have this number n, and we call this the index, right? The thing that is the nth root, right? Like, so this is square root or cubed root or whatever, if this was 2 or 3, right? It's this little number that's sort of outside the square root to tell you what root it is. It's the index. Raised to a power m, like this, okay? So if you have an index of n and a power, so like everything's being raised to a power m, that is the same as x to the power of m divided by n, right? Which if you look, this is the same thing as this. It doesn't matter if the 7th is in the square root or not, actually, right? So it could actually be, or it could actually be the nth root of x to the m power on the inside. These are both the same. They both equal this thing, okay? And so if I try this logic, if I use this logic for part C, I can see that n is the number on the bottom, m is the number on the top. And so this final answer is just going to be the cubed root, the third root, because that is, no, sorry, the second root, or sorry, the fourth root, because that's n is 4. The fourth root of 12 to the 3, right? Or you could rewrite it as the 12th root of, or the 4th root of 12 to the 3rd power. They're both the same. Okay. These are important. This is important if you don't have notes down on this. Next up, we have something that's also a little bit different, but same idea with these radical rules. We want to simplify, but this time we're going to do it by extracting perfect squares, okay? My biggest tip to you, and I will have a list of the first 10 perfect squares on the board, but if you need help memorizing them, here's a quick list. So what I mean by the perfect squares is we have all these countable numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? We have all these. Each one of these has a perfect square that's associated with it, and you find it by taking the number times itself. So 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. And 10 times 10 is 100. This bottom row, these are the perfect squares. Okay? And so what we want to do by extracting perfect squares means find the largest perfect square that is a factor of the inside, right? Of the inside, right? So a factor of the inside number. So in this case, we want to find the largest perfect square that is a factor of 50. Okay. What I mean by factor is I can multiply, or I guess it divides evenly into 50. And so what I would do in your calculator if you're stuck is to just take 50 and start dividing it by these numbers on the bottom, right? You might think 49 because it's the closest number to 50. By the way, the guy died again. Imagine, couldn't be me. Take the number closest to 50, which is 49. That doesn't actually help you though, because 49 can't go into 50, right? Oftentimes it's going to be a number that's below half of it or exactly half of it. Like in this case where I see that 25 can go into 50 and it can go into 50 2 times. And so here's how I would rewrite this. This is the same as the square root of 25 times 2, right? That is the square root of 50 because 50 is 25 times 2. I could even break it up even more to say this is the same as the square root of 25 times the square root of 2, okay? Basically just separating each of these. And the reason to do that is because I know what the square root of 25 is. The square root of 25 is just 5, right? And so this becomes 5 times the square root of 2, and that's your final answer. You know it's your final answer because the only thing left inside of the square root is a number that can't be broken down anymore, right? There are none of these numbers on the bottom, well, besides 1, but that doesn't really matter. There's none of these numbers that can go into 2, right? 4 is too big. It can't go into 2. All right. For these two, you have a couple different options. You can either split it up and do the same process before thinking about multiplying, or what I prefer to do is to just multiply the two things together and get one bigger number in the inside. I have to double check what 24 times 6 is, but I believe it's something like 144, the square root of 144. And here's the reason why you might want to multiply first before breaking it down, right? I could break down 24 into like, 4 times 6, right? I could break that down. I could break 6 kind of into something, I don't know. But the big idea, if you continue dividing these out, you will find that the square root of 144 is just 12, right? If I continue this list, it would be 11, 121, and then 12, 144. And so your final answer is just 12 because the square root of 144 is 12. Okay. Let's try this one on the bottom. Whoop. Oh boy. Let's take all these down. Let's take all these down. Let's take all these down. Let's drop this down. Let's drop this down. Okay. Let's give myself some extra space here. So let's try to figure this one out. And I kind of want to do the same thing. So I want to multiply the insides of the radicals first. So I'm going to leave this 3 out in front. And I'm going to multiply it by 4 times 18, which is, I'm doing this in my head, clearly 72. Okay, the square root of 72. And then what I have to do is just break down what the square root of 72 is. And so I'm going to look at my list, and I'm going to try and find the biggest one of these, the things on the bottom that can go into 72. It's a factor of it. 4 actually can, right? I think it's 4 times 18. I just got that. 9 can as well. It's 9 times 8. But if you continue going, you'll see that 36 is actually the largest one because, and let me just Oh boy, that's not good. Let me just grab all this again, drag you down again. 72 is the same as 36 times 2. So really what this becomes is 3 times the square root of 36 times the square root of 2, right? That's this broken up. 36 times 2 is 72. The reason I chose 36 is because it's the largest perfect square, which means I know what its square root is, right? The square root of 36 is 6, because 6 times 6 is 36. So this becomes 3 times 6 times the square root of 2. Hey, that's the same as 3 times 6 is 18 square roots of 2. And there's your final answer. Okay, so the big idea with these is that you have to just factor out these perfect squares. And then once you're left with the small thing on the inside, like this square root of 2, you're done, right? I can't reduce this anymore, but technically this is simplified over that. And I think it is. Okay, number 7. What happened to number 6? I don't know. Good question. This is very blurry, and I'm only going to do a couple of these. These are things that you know. This is basically combining exponents and things like that, but I just wanted to throw some fractions at you, but I gave them multiple choice. So you have the option to just sort of guess and check maybe. You could plug in some numbers to see if it works, or you can just use some logic, okay? So with these ones, we have to just apply the exponent rules. What we know about the exponent rules is that if you have like bases being multiplied, so in this case, all of the, like this n times n is a like base. It's really, really, hold on, let me see if I can make this any bigger. Okay, that's a little bit better. It's pretty blurry, but sorry. Like bases being multiplied means that you should add the exponents together. Okay, so in this case, we have this problem where the like bases are being added and we have two numbers in front. Well, what's cool about this problem is that I think you can do the multiple choice without even worrying about the fractions, because you know you have to multiply this 3 times 2 together as well. And 3 times 3, like really this is 3 times 2 times n to the 1/2 times n to the 1/4. I just rewrote it in a different order. 3 times 2 is 6. The only one of these answers with 6 is B. So I think that's going to be it. It's a little SAT guess and check strategy, or multiple choice strategy. But let's do it for the sake of doing it. We would just have to add up what this is, right? Because I have a like base, I add the exponents 1/2 plus 1/4. If you need a refresher adding fractions, you need to find a common denominator, which means I'm going to rewrite 1/2 as 2/4. They're the same thing, but now I can just add top to top for the fraction, and that becomes 6n to the 3/4, which, hey, is the answer B. Okay. In 2, they don't give us that much of a hint because there's 2 answers with the number 4. I know that there's going to be a 4 in front though, so we can cancel out C and D. But we do have to figure out which one is which. And we have to add then this fraction together, basically r to the 3/4 times r to the 1/2. Well, the exponent here is going to be them added together. Same logic, 3/4 plus, I'm going to rewrite 1/2 as 2/4 because then they have a common denominator. 3 plus 2 is 5. So it should really be r to the 5/4. And then that 4 out front stays there. That's answer A. Okay. For 3, it's the power to a power rule, which means you multiply. And so all we have to do in this one is take x to the 1/3 and we multiply it by 5/3. Now, multiplying fractions is quite nice. You don't have to find a common denominator, even though we already have one. You just multiply top to top, bottom to bottom, right? And so what this becomes is 5 times 1 is 5. It's x to the 5/9. And that's answer B, right? 5 times 1 is 5. 3 times 3 is 9. So that's your final answer. And then in this case, finally for number 4, another rule we have to worry about, instead of like bases being subtracted this time. Sorry, what? Divided. Being divided. I got ahead of myself. Like bases being divided means you subtract the exponents. So when we multiplied, we added. The opposite of multiply is divide. And so we're going to do the opposite of add, which is subtract. And so really what this becomes is we have this m to the 2/3 over 4m to the 1/2. We have to subtract 2/3 minus 1/2. It's a little tricky. You have to find a common denominator between 2 and 3. In other words, a number that both of these can go into. I think the lowest one is 6, which is just 2 times 3. And so really 2/3 is the same as 4/6, and 1/2 is the same as 3/6. And so my exponent is going to be 1/6. So what I have to find is, because this 4 was in the denominator, it's going to stay there. And so my final answer is going to be m to the 1/6 over 4, which is A, right? If you need a refresher, adding, subtracting fractions, I don't know, ask your parents. They could probably help. Maybe they can't remember. Then if you can't remember, if your parents can't remember, then you can teach them. But otherwise, I don't know, Khan Academy. There's probably some TikToks that help you add fractions. I think I've seen some come up on my page. Just scroll long enough. All right, this is the last question. I think we're almost done. Yeah. We're on number 8, which has to do exactly with the thing that we started with. Isn't life crazy? It's so cyclical, right? It's just a one long loop. And so because of that, I'm going to just take all of this stuff that I wrote at the beginning and use it for this. I need my dragger. There we go. Let's go with the Control G, wait, nope, let me redraw it. Oh, I don't need you actually. Hold on. Erase. Okay, let me get you. I almost could have written it all down again. We go Control G, Control C, Control V until we're here. Look at that. Fits perfectly. Okay. So all of these parts of this equation are things that we can change. They give us a base equation, like a parent function, and then we have to change something to it based on what they say here. So what is this equation? F of x equals 9 to the power x after a translation 2 units down. Well, I know that this value that's outside of my function, just at the end, being added or subtracted, that shifts me up or down. If I want to go down 2, then all I have to do is subtract 2. And there's my answer, right? Not inside, not up top, not in front, just minus 2 somewhere, okay? Same thing, 9 to the power x after 3 units up. Well, I'm going to change that same number. This d value is going to become f of x equals 9 to the power x. And in this case, because we're shifting up 3, it's going to be plus 3. Sorry, I make it purple. Color code, plus 3, okay? Supposed to be equals. And then in these ones, I throw a little bit more at you. I try to get you with a couple at once. The thing that's changed here, this rate in parentheses, that doesn't really affect your translations at all. It just changes what equation you're translating or transforming, okay? And so g of x equals 1/5 to the power x. But I want to translate it 5 units left and 2 units down, okay? Well, I know that the 2 units down is going to be a minus 2 just outside. But from my notes, I saw that horizontal translation happens in the exponent. So up top in the function, and it's opposite, right? So if I subtract is when I go right, but if I add, I go left. I need to go 5 units left. That means I need to add 5 in my exponent. Okay, so my final equation is g of x equals 1/5 to the power of x plus 5, and then minus 2 on the outside. Okay, and then last but not least, we have similar idea, but I threw one final transformation at you, which we have talked about. And it has to do, first, we can do 5 units to the right. I know that anything to the right is going to be in the exponent up top. This time I need to subtract though. So I'm actually going to subtract 5 because I need to go to the right. But then we throw this at you, vertical reflection. Okay, vertical reflection. Well, what is a vertical reflection? Here's what it would look like, right? If you have some graph like this, something like this, a vertical reflection would take each point and put it in the same place, but upside down, right? It vertically takes the points and moves them reflected, right? So it reflects it upside down. So this is a vertical reflection. Is the red, okay? And how you get that in the equation is, well, you have to change your y-intercept to something negative, right? In most of these equations, my y-intercept is going to be positive, but in this case, I need it to be a negative, which means I need to change my starting value to something negative. And the easiest way to do that is to just put a minus sign in front, right? If this a value is negative, that means your graph's going to be reflected. And so what you do is you just throw a minus sign out in front of whatever you're multiplying by your rate, right? That reflects it vertically. But it doesn't necessarily change the starting value. It just moves it down and makes it go down like this. And then finally, we have a translation 3 units up. That means plus 3 at the end. Okay? And that's it. There's module 3, topic 1, all about exponents, their graphs, how you set up the equations and stuff. We're going to do more like calculations based in the next unit. But otherwise, good luck studying. Ask any questions. You can leave a comment. You can email me. If you're watching this on Wednesday, sorry you might not have a calculator or anything, but good luck. Okay, and I'll see you guys later.